this is the second part of the solutions for the problem set about vector spaces. We're dealing with the set S8 that consists of cubic polynomials for which P of the polynomial evaluated at 0 is equal to the polynomial evaluated at 1 equals to the polynomial evaluated at 2. The polynomial evaluated at 0, we know that is just the constant term. So if I take the most general vector in P3, that's ax cubed plus bx squared plus cx plus d. P of 0 is when I'm going to plug 0 for each x and I just get the constant term. P of 1 is just, if I plug 1 for each x, I get a plus b plus c plus d. And if I evaluate the polynomial at 2, I get 8a plus 4b plus 2c plus d. And now from the fact that P of 0 is equal to P of 1, I get that a plus b plus c plus d is equal to d. And then d and d cancels out for each value of d, okay, from where I get that a plus b plus c is equal to 0, or simply if I choose to express c is equal to negative a minus b. And from the fact that P of 1 is equal to P of 2, I get that a plus b plus c plus d is equal to 8a plus 4b plus 2c plus d. Again, d cancels out for each value of d, and then I get that 0 is equal to 8a minus a is 7a plus 4b minus b is 3b plus 2c minus c is c. So 7a plus 3b plus c is 0. But c is equal to negative a minus b, so I get 7a plus 3b minus a minus b is 0. From here, 6a plus 2b is equal to 0, or simply bring b on this side, and I get that b is equal to negative 3a. Okay, well, if b is equal to negative 3a, then c is equal to negative a minus 3a, from where I get that c is equal to 2a. So I have expressed c and b in terms of a, then take the general cubic polynomial and express it with these conditions here. Okay? Knowing that d is free, because d will cancel out for any constant, for any value we give it. So p of x is equal to ax cubed plus, instead of b, I write that that's minus 3a times x squared, plus, instead of c, I write how much I have gotten in terms of a, that's 2a times x plus d, and now simply factor a for each term and you get x cubed minus 3x squared plus 2x plus d times 1, of course. Since S8 can be expressed as a span of vectors in P3, where those vectors are x cubed minus 3x squared plus 2x and 1, we conclude that S8 is a subspace, and its bases are just these two vectors, this one and the vector 1. Its basis is x cubed minus 3x squared plus 2x and 1. Somebody during the class asked me whether we can put this in a matrix, and of course we can. We'll get the same solution, but be careful what you put in matrix. So we have the two equations, that's a plus b plus c is equal to 0. Okay, so I'm solving for a, b, c, and d, and I have a homogeneous system 1, 1, 1, 0, and 7a plus 3b plus c is 0, so 7, 3, 1, 0. This will be row equivalent to 1, 0, negative 1 half 0, 0, 1, 3 over 2, 0. And as you can see, D is free, C is free, B is equal to negative 3 over 2c, and A is equal to 1 half c. So from here, if I express ax cubed plus bx squared plus cx plus d, I will get 1 half cx cubed minus 3 over 2 cx squared plus cx plus d factor c here, and you get 1 half x cubed minus 3 over 2 x squared plus x plus d. Now again, you've got this polynomial right here in the basis and 1. Of course, I can obtain absolutely the same expression here if I can factor 1 half c, and then I get x cubed minus 3x squared plus 2x plus d. So you can do either this or this. The next question is this quadratic polynomial for which the constant term is greater or equal to 0. Obviously, the 0 vector, which is simply the number 0, is greater or equal to 0, so the 0 vector is in S9. Is this closed under a vector addition? Yes, it is, because if you take two vectors p1 in S9, which means that the constant term is greater or equal to 9, and p2 in S9, so another quadratic polynomial whose constant term is greater or equal to 9, the sum is going to be also the constant term of the sum of these two polynomials is also going to be greater or equal to 1, right? So if p of 1 is equal to ax squared, a1x squared plus bx, b1x plus c1, such that c1 is greater or equal to 0, and p2, which is a2x plus b2x plus c2, such that c2 is greater or equal to 0, then the vector p1 plus p2 is going to be a1 plus a2 x squared plus b1 plus b2 x plus c1 plus c2, but this is also going to be in S9 because c1 plus c2 is going to be greater or equal to 0, because a sum of two positive numbers is going to be positive. But so this means it's closed under vector addition, but it's not going to be closed under scalar multiplication. Simply take p of 1 and multiply it by negative 1. Let p be x squared plus x plus 2. Obviously in S9, negative p is equal to negative x squared minus x minus 2. Not in S9, since negative p evaluated at 0 is negative 2, and that is strictly less than 0, not greater or equal to 0. So this set is not closed under scalar multiplication, which makes it not a subspace. Okay, so we are now in the vector space of 2 by 2 matrices. Okay, so let's take a general 2 by 2 matrix. And let's see the left-hand side of the condition, 0, 1, negative 1, 0, times A, B, C, and D. This is 0 times A, 0, plus 1 times C, C, 0 times B is 0, plus 1 times D is D, negative 1 times A is negative A plus 0, negative A, and negative 1 times B is negative B because we add 0. On the other hand, this has to be equal to X, the matrix X, A, B, C, D, times 0, 1, negative 1, 0, and that gives us A times 0 is 0, minus B, A plus 0 is A, 0 minus D is negative D, and C plus 0 is C. So these two matrices have to be the same. C, D, negative A, negative B is equal to negative B, A, negative D, C, and we compare each corresponding entry. So from here, C is equal to negative B, D is equal to A, negative A is equal to negative D. But as you can see, if you multiply this by negative 1, we actually get the same condition here. So simply A is equal to D, and the last one, negative B is equal to C. Negative B is equal to C is literally the same condition as C is equal to negative B. So basically we are talking about the 2 by 2 matrix A, B, C, D for which this is satisfied. Is equal to A, B, C is negative B, and D is A. And this can be written as A, 0, 0, A, plus 0, B, negative B, 0 is equal to A, 1, 0, 0, 1, plus B, 0, 1, negative 1, 0. So since S10 can be expressed as a span of vectors in M2 by 2, S10 is a subspace whose basis consists of these two vectors. Obviously the dimension of S10 is 2 because we have only two vectors in the basis. The next set is the set of all the 2 by 2 matrices where all the 2 by 2 symmetric matrices. So let's just recall that A is symmetric if A is equal to A transpose. Okay, so let's see what does this mean. This is the general 2 by 2 matrix. If I find its transpose, it has to be equal to A, B, C, D transpose, and the transpose is A, C, B, D. So if we compare these two matrices, okay, what do we have? That A is equal to A for any value of A, D is equal to D for any value of D, right? So A and D are free, so all I have that B is equal to C, right? B is equal to C and C is equal to B, which is the same condition. Sorry, B is equal to C and C is equal to B, my bad, sorry about that. From here it follows that A, B, C, D can be written as A, B, B, because B is equal to C, D, and this is A, 1, 0, 0, 0, plus B, 0, 1, 1, 0, plus D, 0, 0, 0, 1. And again, you write the conclusion, since S11 can be written as a span of 2 by 2 matrices, S11 subspaces is 1 0 0 0 0 1 1 0 0 0 0 1. The dimension of S11 obviously is 3. You should try to practice showing that the closures are satisfied. For example, the zero matrix. Right? If you have questions to show that the zero matrix is in S11, the zero matrix is just 0 0 0 0, which is equal to 0 0 0 0 transpose, which means that the zero vector is in S11. Take two symmetric matrices A, so let A and B be in S11. Okay, so two symmetric matrices, right? Then A plus B is equal to A plus B transpose. Why? Because A plus B transpose is A transpose plus B transpose, and this equality holds from here. Since A is in S11, that means A is symmetric, and since B is in S11, that means B is symmetric, so A is equal to A transpose, and B is equal to A B transpose, so A plus B must be equal to A plus B transpose, which means that S11 is closed under vector addition. And to show that S11 is closed under scalar multiplication, so let A be symmetric, okay, then K times A will also be equal to K times A transpose, because by properties of transpose matrices, this is K times A transpose, and this equality holds because A is already equal to A transpose since A is symmetric. So this means that S11 is closed under scalar multiplication. So this is, if you're being asked to go over the three conditions, this is what you do. The 12th set, S12, is the set of all the 2x2 invertible matrices, and we will disprove this by showing, we will show that this is not a subspace. This fails even with the first condition. Show that the zero element is not in S12, so the zero element is not in S12 since 0 0 0 0 is not invertible. Okay, and why we know that it's not invertible, because this, the determinant of this vector of this matrix is 0, and we know that matrices with 0 determinant are not invertible. Okay, to show that it's not closed under vector addition, well, take two particular vectors from S12, that means two invertible 2x2 matrices. Let's go with the easiest one, with the identity matrix. Obviously, this is an invertible 2x2 matrix, and let another matrix 0 1 1 0, which is also in S12. How do I know that? Well, the determinant is not 0, so that means that this one is invertible. But 1 0 0 1 plus 0 1 1 0 is equal to 1 1 1 1, and this is not in S12 since 1, 1, 1, 1 is singular, is non-invertible, because and I don't have any more electricity at home, which this is the funniest thing that has happened to me. So yes, I'll see you in the third part of this video, which I don't know when it will happen. See you soon, I hope.